Welcome back to the Calculus AP course. Hopefully you've had a chance to take a look at the Calculus AP introduction. And the purpose of that introduction was to give you some idea of the content of this course. And today we're going to take a look at day one, namely the rates of change and limits. So in this first example, you're driving with a broken speedometer, which would be against the law. However, the odometer readings have been taken over the trip show that in these various times, measured in hours in the first row, the displacement from where you started the trip is mentioned in the second row. And so the question then is, if the speed limit was 80 kilometers an hour, were you ever speeding? And so what would we need to calculate? Well, let's take a look. We're going to calculate from time 0 to time 1 and take a look at what the average rate of change was. So the average rate of change is determined by taking a look at the speed at t plus h minus s of t all over t plus h minus t. And so you can see that this simplifies to s of t plus h minus s of t all over h. So from time 0 to 1, our average rate of change would just be the distance at the displacement at 1 hour minus your displacement at the 0th hour, all divided by 1 minus 0, which is 1. And if you notice in the table, s of 1 is 133 minus s of 0, which was 62, all divided by 1, and that comes to 71 kilometers an hour. So the question was, were you ever speeding? Well, certainly in that first hour we were not. The average rate of change was 71. You may have been going higher, you may have been going lower, but the average was 71. Now, after calculations of the average rate of change from 1 to 2 and 2 to 3 and 3 to 4, it appears at no time were we speeding. But in fact, that would be false, because during any one of those intervals, you could have been going higher than the average. So for example, in time 1 to 2, we could have been going at 85, but the average was 87. So we may very well have been speeding, but you certainly can't tell by looking at the average rate of change. Okay, so we can't tell. They can't tell if speeding occurred. Now, another option we have occurred is we're going to take a look at another example here where we're going to take a look at average rate of change and then contrast that with instantaneous rate of change. In the second example, a pebble was thrown off a cliff, and given that it will have a parabolic path, the model that's modeling the distance after t seconds is given by 80 minus t squared. First thing we want to do is to calculate the average velocity of the pebble between times 1 and time 3. So to calculate that, the average velocity, again, would be s of 3, namely the displacement or the distance traveled after 3 seconds, minus s of 1, oops, that's supposed to be a 1, all divided by 3 minus 1. And if you put 3 into that equation, you get 35. If you put 1 into that equation, you get 80 minus 5, which is 75, all divided by 2. And that works out to negative 40 divided by 2, which is negative 20 meters per second. If we now calculate the average velocity of the pebble between 1 second and 1.5, the average rate of change, remember, would be the displacement at 1.5 minus s of 1 divided by 1.5 minus 1. And so that comes to 68.75 minus 75, all divided by 0.5. And that works out to minus 12.5 meters per second. And the question is, why are the answers above different? Well, quite aside from the fact that they were taken over different intervals. The first one was between 1 and 3 seconds, whereas the other one was between 1 and 1.5 seconds. The longer the interval, the faster the object is accelerating towards the ground. The minus sign for both of those answers indicates that the object was traveling towards the ground. Now, this might be a good time for you to pause the video and see if you can determine what the average velocity was between these time intervals. The intervals are much shorter this time. As you can see, in the first interval, it's only 0.1 of a second, a difference between 0.01 in the second one and 1/1000th of a second in the third calculation. So go ahead, pause the video, and determine what these are. All right, if you've returned, this is what you should have found. This one was negative 10.5. Oops, just a second here. 10.5. This one was 10.05. And the last one, negative 10.005. Now, as the interval is getting smaller, as in, going down this column, the average velocity is starting to approach negative 10 meters per second. We call this the instantaneous velocity. Instantaneous. So in a car, for example, in the previous example, if you wanted to determine if you were speeding or not, all one has to do is to take a look at the speedometer, assuming it was working. And the speedometer would give you the instantaneous velocity. So we can get instantaneous velocity if we make this interval small enough. Now, as I indicated in the previous calculation there, that the average velocity on an interval is determined by just taking the distance at a particular time, minus, in this case, s of 1, and then dividing by 1 plus h minus 1. Now, if we do that, let's do this for, we're going to do this for this example here. And so this becomes 80 minus 5 times 1 plus h squared. And then we're subtracting that same s of 1, which would be this displacement function evaluated at t equal to 1. So that would be 80 minus 5. And we're dividing all this by 1 plus h minus 1 would just be h. And now if we get rid of those brackets by expanding those binomials, we end up with minus 5h squared minus 10h minus 5. And then this is 75 in here, so minus 75 all over h. And now we notice that the AD and the -5 -75 cancel each other. And if I were to factor out that h, I end up getting -5h minus 10 all over h. And the h's cancel. And so we get the result that this is just equal to -5h minus 10. Now, if we were to let h become, as you saw in the previous example here, where the time difference there, we were letting it get smaller and smaller. And that's represented by h in this example. And so if we were to take a look at what happens as h becomes 0, h goes to 0, this expression becomes -0 minus 10, which is -10, in this case, meters per second. So as h approaches 0, we get the instantaneous velocity. We started with the average velocity formula, but then as we let h go to 0, we end up getting the instantaneous velocity. So instantaneous velocity, whoops, I see a spelling mistake there. Velocity is defined to be a limit as that difference in time approaches 0 of delta s over delta t. And you saw that shown in the previous example. And then we saw that that became -10 in that previous example. Now, to fully understand how limits work, one needs to know some of the properties of limits. The idea of a limit is what does some function approach as the variable approaches various values. So in all of these examples, x is approaching c, and we want to take a look at the limit of, it says, if the limit of f of x as x approaches c is some limit, L1, and the limit of g of x as x approaches c is some other limit number, L2, then the following limit properties hold. Namely, the limit of a sum or difference is just simply the sum or difference of the limits. The limit of a product of two functions as x approaches c would just be the product of the limits. The limit of a quotient is the quotient of the limits, assuming that L2 is not 0, of course, because that would be undefined. The limit of a function raised to a power is just the limit raised to that power, known as the power rule. And the last one is if the limit of a function raised to a rational exponent would just be that limit raised to that same rational exponent. These may seem obvious or intuitively true, but just so that they're laid out so that you know how to use them. Now, let's take a look at how to evaluate limits. It says the limits, it says the limit of f of x as approaches c is equal to just f of c. In other words, if you can take the limit by just making a substitution, then you should. So for example, if we take a look at what is the limit as x approaches 2 of 3x squared minus 5x plus 1, all this is saying is what number is y of f of x approaching as x is approaching 2? Well, we can figure that out just by substitution here. So that would just be 3 times 2 squared minus 5 times 2 plus 1. And so that becomes 12 minus 10, which is 2 plus 1, 3. Okay, so this simply says that as the function is, as the x is approaching 2 on this function, the y value is approaching 3. Let's look at another example. Let's look at the limit as x is approaching 1 of x cubed minus 3 all over x minus 1. So to understand the concept of a limit, the function value may not actually exist at that point. In the previous one, that was a parabola which is defined for all x, And so that one makes sense. But for this one, this function is not defined. This is a rational expression. It's not defined when x is equal to 1. And yet, the limit does exist. So we've got here that the limit of f of x over g of x, remember that was one of the properties, is just simply the quotient of the limits, assuming that the bottom is not 0. Well, initially it looks like it's 0. However, the top being a difference of cubes factors. And what does it factor into? Well, x minus 1. And then this would be x squared plus x plus 1, all divided by x minus 1. And now something nice has happened. The x minus 1's cancel. And so this ends up being the limit as x approaches 1 of x squared plus x plus 1. And if we make the substitution like we did in the previous example, we end up getting 1 plus 1 plus 1, which is 3. So what this is indicating is, even though this rational expression is not defined at x equal to 1, the y value, or f of x, is approaching 3 as x is approaching 1, even though f of 1 is not defined. One-sided and two-sided limits. Let's look at an example of this. I'm going to draw a function here, which is a piecewise function. And let's say this goes from here to here, it's linear, and then maybe it's a parabolic from there onwards. And let's say that this is at positive 3, and this is negative 1. And this is the point where these two curves meet. Now, if we take a look at the limit, for example, as x is approaching, in this example, as x is approaching negative 1 from the right-hand side. So this notation, negative 1 with the plus written like that, or superscript of 1, indicates what the limit is. The limit is as x approaches negative 1 from the right-hand side. So if you're looking along coming from the right-hand side, this function appears to be, of f of x, is approaching 3. If we look at the limit as x is approaching negative 1 from the left-hand side, in other words, along this linear piece, as x is approaching negative 1 of f of x, is also equal to 3. Now, I meant to say that there was a hole here. In other words, maybe the function is not actually defined. And so even though if the function isn't defined there, the fact that these two limits both are coming down to the same value means that the limit does exist. Okay, so these are the same. And so the limit exists. So the limit exists. Even though GH, f of negative 1 may not be 3. For example, this is a piecewise function. F of negative 1 could be defined to be this point down here, for example. And so in this case, even though because the two one-sided limits are approaching the same value, we say the limit does exist and is 3 in this example. All right, let's take a look at this one. Well, as before, the top factors into limit as x approaches 2 of x minus 1, because that's the difference of cubes, which factors into this, all divided by x minus 2. Now, in this case, I can't evaluate this limit by substitution because nothing's canceling. And because it doesn't cancel, we say that the limit does not exist. Okay, and I'll abbreviate that as DNE in any further discussions of limits. Now, I'm going to show you something that, and we'll discuss later on in the course, but to give you an idea about how to handle something like this. What is the limit as x is approaching 0 for sine x over x? So I've plotted the function there, sine x over x, and you can see that as x is approaching 0, namely, from both left-hand side or the right-hand side, the two one-sided limits would be equal to each other. And so the y value is approaching 1, even though the function itself is not defined at x equal to 0. So when we're doing this, and you'll see this later on in the course, that if we try and evaluate this, and you try and put 0 in there, we end up getting the sine of 0, recalling, the sine function looks like this. And so the sine of 0 is just 0. So we end up getting 0 over 0. This is referred to as being indeterminate. Indeterminate. And we're going to learn about derivatives later on, and using a thing known as L'Hopital's rule, which I'll abbreviate looking like that. We'll learn about L'Hopital later. We can take the derivatives, which you'll also learn about later. And the derivative of sine x is cos x. And the derivative of cos x is equal to 1, of x rather, is equal to 1. And so this limit is just equal to the limit as x approaches 0, using L'Hopital's rule of cos x over 1, which would be cos x. And if you recall, the cos x function looks like this. And so as x approaches 0, cos x is approaching 1. And so this answer is 1. Now, there's another way of seeing this, and it has to do with what's known as the sandwich theorem. Hence the picture of the sandwich. So what does this theorem say? Well, I've got the line y equals, or h of x equals 1 up there. I've also plotted the cos function, and you notice as cos x is approaching, as x is approaching 0, g of x is approaching 1. And so these functions are well defined, y is equal to 1, and the cos function. The sine function happens to fall right in between them in this region. And so the limit of 1 as x approaches 0 is 1. We can see that because it's always 1. The limit of cos x as x is approaching 0 is 1. We can see that on the green curve. And the sine function is always falling in between, certainly in the region where x is approaching 0. So what the theorem says, the sandwich theorem states that if a function f of x has values which fall between two other known functions which have limits as x approaches c on some interval, then the limit of that function as x approaches c is also L, even if f of c is not defined. And so our sine x function, or sine x over x, is sandwiched in between h of x equal to 1 and h of x equal to cos, or g of x equal to cos. And since it falls between two well-defined functions at x equal to 0, the limit does in fact exist and is equal to 1. So just another way of taking a look at that limit that we earlier did using derivatives and L'Hopital's rule, which will be covered later on in the course. All right, let's take a look at some more limit examples. Some of them are very straightforward because it's just substitution. You might want to pause the video at this point and see if you can do these on your own. You can do them by substitution, and just pause it here. See if you can evaluate these at x equal to 4 for the first two examples, and then you can see the limiting values in the second two examples. So pause the video here and take a look at this and see what you get. All right, if you've returned, you should have found that this one is equal to 5 just by substituting 4 into that. Likewise, this one is also equal to 5 because it ends up being the square root of 24 plus 1, which is 25. Root of 25 is 5. This one works out to be negative 1 plus 1, so that's 0. Root of 0 is 0. And now this one requires some discussion. If you factored this, which you should have, you should always try and factor to see if something nice is going to happen. So in this case, as t is approaching 2, and if we factor the quadratic at the top, we get t minus 1 times t minus 2. This is all over t minus 2, minus 2. And then the t minus 2's cancel. And so really what we're looking at is the limit as t is approaching 2 of t minus 1. So we're looking at the linear function t minus 1 as t is approaching 2. Well, as t approaches 2, 2 minus 1 is 1. So the answer here is 1. Now, what does this mean graphically? Let's take a look. We found by doing the factoring and the canceling there that the function, that quadratic divided by linear, actually has linear behavior. And so it looks like this. There's t minus 1, right? Has a y-intercept of negative 1. But we said that the limit as t approaches 2 is equal to 1. What does that mean? Well, as t is equal to 2, which would be right there, y is approaching 1. And so there's really a hole here. This is a hole. Because if you look at the original function, it wasn't defined for t equal to 2. And so f of 2 is not defined. Right? F of 2 is a hole. Is not defined. But when we take a look at the limit of this linear function as x is approaching 2 is 1, as we saw in the algebraic calculation here. Okay, so hopefully by now you understand what we mean by limit, i.e. the value that the function is approaching, but not necessarily there. Even though the function does not exist, the limit can exist. All right. Here's some other examples. Again, you may want to pause this and see if you can tackle this on your own. All right, if you've come back, hopefully you have, we should be able to factor this. This is a difference of cubes. And, oh, sorry, not cubes, difference of fifths. But the bottom is also got a difference of fifths in the factoring of it. So we look at the limit as x goes to b. The top is x to the fifth minus b to the fifth, all over. And the bottom factors into x to the fifth minus b to the fifth. It sort of looks like a difference of squares. And x to the fifth plus b to the fifth. Okay, and the x to the fifth minus b to the fifth cancel, and so we just end up with the limit as x goes to b, approaches b I should say, of 1 over x to the fifth plus b to the fifth. And if we let x approach b, then this becomes a b to the fifth on the bottom plus another b to the fifth, which is just 1 over 2b to the fifth. Now, this one was a little bit challenging unless you remember about dealing with conjugates from a previous year in your education. There's nothing appears that we can do here to get rid of the problem that t is approaching 0 unless we multiply the top and bottom by the conjugate of the numerator. And you remember the conjugate is just the root of t plus 2 plus the root of 2. And so we'll multiply the top and bottom by the conjugate of the top. This is sometimes referred to as rationalizing the numerator. And so this becomes the limit as t approaches 0. And this just looks like the factors of a minus b times a plus b, and which you'll recall is just the same as a squared minus b squared. And so I end up with a squared, which would be t plus 2, minus b squared, which would just be 2, all over t, times that t plus 2 plus root 2. And now you can see that the 2's cancel. And now the t can divide into the t, leaving us with a 1 on the top. And so we end up getting the limit as t approaches 0 of 1 over root t plus 2 plus root 2. And this guy is well defined because we can now let t go to 0, and we simply end up with 1 over 2 root 2, which ends up being just root 2 over 4 if you multiply top and bottom by root 2. Hopefully you got that answer. Well, that takes care of our lesson on limits. So thank you for watching Rates of Change and Limits, and hopefully we'll see you soon in the next lecture. Bye.